Hey everybody, in this video, we're going to be talking about using trapezoids to estimate the area under a curve. Let's first review the concept of what is an area under a curve. The area under a curve is the area between the curve and the x-axis on an interval. As a very simple case, let's consider a function that's a horizontal line. As you can see, the area forms a rectangle, and the area of that rectangle is the height f of x times the width b minus a. But how do we find the exact area under a curve that varies in height? This is actually a big question in calculus, and we'll discuss this in a future video. But one way that we can approximate the area under a curve is by using trapezoids. In this diagram, I've divided the region from A to B into 3 evenly spaced trapezoids. The areas of the trapezoids are shaded in green. As you can see, the sum of the areas of the trapezoids is an approximation for the actual area under the curve. Some of the trapezoids underestimate the area under the curve, while others overestimate the area. From geometry, the area of a trapezoid is 1/2 h times the quantity of base 1 plus base 2. Now we can find the areas of each trapezoid. Note that the height of each trapezoid is on the x-axis. In order to find the bases of each trapezoid, we need to find the function values, f of 0, f of 1, f of 2, and f of 3. In order to find the height of each trapezoid, we need to figure out how far apart each trapezoid is spaced. In other words, we need to find delta x, and delta x is b minus a over n. A and b are the endpoints of the interval. So in this case, a is 0 and b is 3. Since we have 3 trapezoids, n equals 3. So delta x is 3 minus 0 divided by 3, which equals 1. The height of each trapezoid is 1. Now we can write an equation that represents the sum of the areas of the 3 trapezoids. We're going to call this t sub 3. This notation means that we're approximating the area under the curve using 3 trapezoids. The area of the first trapezoid is 1/2 times the height times the quantity of f of 0 plus f of 1. The area of the second trapezoid is 1/2 times the height times the quantity of f of 1 plus f of 2. The area of the third trapezoid is 1/2 times the height times the quantity of f of 2 plus f of 3. Now we can factor out a 1/2 h, and our equation simplifies to 1/2 h times f of 0 plus f of 1 plus f of 1 plus f of 2 plus f of 2 plus f of 3. Then we can combine like terms, and we get 1/2 h times the quantity of f of 0 plus 2f of 1 plus 2f of 2 plus f of 3. Note that base 1 of the second trapezoid is base 2 of the first trapezoid. And note that base 1 of the third trapezoid is base 2 of the second trapezoid. That's why all of the middle terms are counted twice. The only terms that aren't counted twice are the left base of the first trapezoid and the right base of the last trapezoid. Now remember earlier, we found the height of each trapezoid, which is 1, so we can plug this in, and then we'll have the final equation that represents the approximate area under the curve using 3 trapezoids. If we need to get a final numerical value, we can just calculate f of 0, f of 1, f of 2, and f of 3, and then just do the arithmetic according to the equation. By using only 3 trapezoids, we get an approximation of the area under the curve, but it's not a very good one. But if we have more trapezoids, we'll get a better approximation. This leads us to the trapezoid rule, a rule that lets us find the approximation for the area under a curve using n trapezoids. The trapezoid rule can be expressed by this equation. T sub n equals 1/2 times the height, which is delta x, times the quantity of f of x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 2 plus all the way down to f of x sub n. Note that all the middle terms are doubled. Now you may encounter another form of the trapezoid rule, and I don't want you to be fooled when you see it. Sometimes what happens is the 1/2 gets distributed inside the parentheses. That means the first term becomes 1/2 f of x sub 0, but the 1/2 would cancel with all the 2's from all the terms that are doubled. And then when we get to the end, we're going to have 1/2 f of x sub n. In any case, both formats of the trapezoid rule will lead you to the same answer. Let's do an example problem. Use 6 trapezoids to approximate the area under f of x on the interval 0, 3. Just set up the equation and don't actually solve. The first thing we need to do is figure out the delta x, the height of each trapezoid. Remember, what we're going to do is take b minus a over n, where a and b are the endpoints of the interval. So in this case, it's going to be 3 minus 0 divided by 6 because we want 6 trapezoids, and that equals 1/2. Now that we have delta x, we can figure out all of the f values that we're going to need to get the bases of each trapezoid. Since all the trapezoids will be spaced 1/2 unit apart, then we're going to need f of 0, f of 1/2, f of 1, f of 3/2, etc. until we reach the right endpoint. Now we can write our equation. T sub 6 equals 1/2 delta x times the quantity of f of 0 plus 2 f of 1/2 plus 2 f of 1 plus 2 f of 3/2 plus 2 f of 2 plus 2 f of 5/2 plus f of 3. Note that all of the middle terms are doubled. Then we can substitute delta x into the equation and multiply it times the 1/2 that's already there to get 1/4. And this equation here is the setup that we can use to figure out the approximation of the area under the curve using 6 trapezoids. We could plug this into a calculator to solve for all of the function values and get a numerical answer. Let's finish this video with a few trapezoid rule tips. The first tip is that we are using trapezoids that are spaced evenly apart. In other calculus problems, you may have to approximate the area under a curve using trapezoids that are not evenly spaced. But we'll save that for a different video. Next, remember that to find the height of each trapezoid, we need to use delta x, which is b minus a over n. Finally, I want you to be aware that there are n plus 1 terms in a trapezoid rule equation. In the last example, we approximated the area under the curve with 6 trapezoids. 6 is our n. But there are 7 terms in the equation. This is a tip that you could use to help you check your work and make sure you have the correct number of terms when you set up a trapezoid approximation equation. Well, that's it for now, so keep on practicing. And that's how you rock calculus!